Welcome back to the next video, everybody. Today's video will be a brief one, just a little bit about derivations from the algebra geometric point of view. Okay, so let G equals spec A be an affine R group scheme. We'll let I be its augmentation ideal. Remember, that's the kernel of the co-unit map. And we'll let M tilde, as usual, be the co-multiplication map from A to A tensor A. We'll let pi be the map sending A, which remember we can decompose as R dot 1 plus I. So we'll set pi will go from A to I mod I squared. So it's the R linear map that just kills R1 and projects I basically, and then mods out by I squared. Okay. And so if M is an A module, any R linear map D, let's say from A to M, satisfying the product rule, the Leibniz rule, is called an R linear derivation on A. Okay, so it behaves very much like a derivative does. Okay, so proposition one, we'll let M be an A module, and psi from M tensor A to M will be the map giving the action of A on M. The map that sends lambda to psi compose quantity, lambda compose pi, tensor ID, all compose M tilde is an isomorphism actually from R module maps from I mod I squared to M with R linear derivations from A to M. Okay. And so what you have here, if you want to draw it out, is you have something like this. So you've got A going to A tensor A via M tilde, right? And then you have that going to M tensor A via lambda compose pi tensor ID. And then you have that going to M via psi. Okay, so that's your map. The map that sends lambda to this composition is the isomorphism. Okay, and so this makes sense, right? Like, what should derivations do? They should locally linearize. In other words, kind of on I, you should kill squares, right? I mean, that's what derivatives do. They linearize objects. Okay, so corollary, the map pi tensor I decompose M tilde from A to I mod I squared tensor A over R, and we call this guy here, by the way, omega 1 of A over R. That's a universal R linear derivation for A. What I mean by that is every R linear derivation from A to M factors through this universal derivation. So in other words, if you choose M to be kind of, I mod I squared, then you get the universal R linear derivation. This is, of course, a universal object. So it's unique up to unique isomorphism. This factorization here is unique in everything. Okay, omega 1 of A over R is called the module of Kähler differentials for this setup for A over R. And for a proof of all this stuff, you can see like the Kills notes on algebraic geometry, chapter 21. You can probably see Hartshorn. Washington's Introduction to Affine Group Schemes, 11.3 talks about this. This is covered kind of everywhere. This is just standard algebraic geometry stuff. And the last thing we want to talk about today briefly is right invariance. So we'll let A be an R algebra, and we'll let G be spec A, and we'll let D be a derivation from A to A, an R linear derivation. For any R algebra B and any X in the B valued points of G, we'll define D of X to be X composed D, which of course is, if you draw it out, a derivation from A to B over R. And we'll just say D is right invariant if it has right invariance, if X plus D of X quantity times Y is XY plus D of XY for all XY in the B valued points of G, so G of B. And so proposition two, can we characterize these right invariant differentials? Sure. So let D be an R linear derivation from A to A. And we'll let lambda from I mod I squared to A be the R linear map corresponding to D as per the previous proposition under that isomorphism. Okay. Then it turns out D is right invariant if and only if the image of I mod I squared under lambda is just in the R dot 1 factor of A. Remember, A is R dot 1 direct sum I. So if the image is just in R dot 1, that's the same as D being right invariant. Okay. And when this happens, epsilon sub A composed D happens to be lambda composed pi, right? And so what we have there is we have, let's see, we have a map from A to A given by D, right? Then we have, I guess, epsilon sub A going to A. And then we have A going to I mod I squared via pi. And then that's going to A via lambda, right? So you can see that, where is that? You can see that up here. So lambda is an element of here where M is A. And so the last thing I want to say is that D is the unique invariant derivation on A such that D of F is equivalent to lambda times pi of F mod I for all F and I. Okay, and so for proof of this proposition, you can see CSS page 132. Okay, and so next time we'll talk a little bit about passage to quotient. So I'll see you then, and thanks for watching.